Hello there. Welcome to Actual Electrical Contact with me, Jamie Bladen. Now, I'm just reading this book, Electric Motors and Drives, Fundamentals, Types and Applications by Austin Hughes and Bill Durry. It's a fantastic book on motors, however, it is very thick and you're probably such a lazy bastard. You can't be asked to read this. Also, it's mainly about the science and stuff behind motors, although it is an excellent book if you get into motors. However, a lot of people just say to me, what about motors? How do motors work? I ran a whole course on motors last week and people are still asking me about it. So I'm going to go through some of the basic things with motors in this series to cover. Not something as complicated as one behind me. This is the Star Delta. This is the Billy Big Bowls of all motor starting systems. Pretty much redundant now because of another type of motor starting system. But what I'm going to cover is the fundamental principle of motor starting, which is the holding contact, which you'll find in the most common type of starter there is, the Dole starter. So let's put this book down and have a look at it. First of all, let's get rid of the Star Delta. This is the big one you're going to work towards that you don't see anymore, but it's the challenge. And let's go and get something a little bit more simple. Let's just explain the basic things that are in a Dole starter. If you're on YouTube, there'll be a picture on here because I forgot to bring the Dole starter prop with me, so I can't show it to you. So watch on YouTube and there'll be a picture of a Dole starter there. Probably a picture of me holding a Dole starter, but I've got the basic components that are within it. Let me grab them and let me show you what they are and what they do in the game of the Dole starter without knocking my camera like I was just doing then. And again. And again. This is an electric motor. This is an electric squirrel cage motor. 3-phase, whatever you want, I don't care. It could be this big. It could be the size of a Ford Fiesta. This is the asset. This is what you want. You don't care about any of the other stuff like what you can see behind me. All you care about is this. And if you just put 3-phase into it, it will spin round like Noah's business and give you the rotation you want for you to do exactly what you do with it. However, if anything goes wrong with the motor itself, the cooling, the bearings, the cabling, or whatever's being used on this for the drive end, the motor will be forced to overwork and it will damage itself and you will lose the expensive asset that is the motor. But also, there's no difference having a motor that's plugged into 3-phase. You want to be able to control it. And the Dole starter does all of those things. That's its thing. That's its thing in life. It wants to start and stop the motor and protect it. Let's show you what a Dole starter is made up from. So if you're on YouTube, there's a picture of me holding a Dole starter. That particular Dole starter in that picture is the cheapest Dole starter you can get off eBay, right? Just an example. And a lot of people consider that those plastic boxes with a red and green button on the front are a Dole starter. They are not, however. The Dole starter, the direct online starter, is within it. And the bit that does the starting and the protection is inside it, although you'll see lots and lots of those kicking around because they're a simple way of controlling and protecting a single motor. However, the actual important parts of a Dole starter are here. I'm going to show you what each one is. Now, you don't have to have all of these, but there's 2 of them that you will have, and I'll start off with those. You might have a container, an adapt box, or some sort of box for it, yeah? It might be in a control panel with 500 other Dole starters, who knows? It might have a start and a stop button on it. I know it's blue, I haven't got a green one here, but it doesn't have to have them. The Dole starter comprises mainly of these components here, and I've got a couple of different ones, yeah? There will be some sort of overload that can look like this. That is to protect the motor from overcurrent in amps, and there'll be some sort of contactor that might look like this. But I'm showing you these ones for a reason. It's because these ones connect together like that into an assembly which basically forms the Dole. Do they connect together properly in assembly? Yeah, they do. That's tucked in there. Is it upside down? I don't know. Anyway, it goes in there like that. That is the basic Dole starter. An overload and the protection and the control bit, the contactor. Right, they can look like different things. You might get one that looks like this. This is called a Telemechanique or a Schneider. It's called a GV2. You might get one that looks like that. They're very common. And I'll show you a load on the board behind me now. So there's a Dole starter, look, there's the contactor, and there is the overload. It's quite an old one. That is made by... Who's that one made by? I don't know. I should look for a starter code. Anyway, it's old. You got the Siemens one. Again, that's got an auxiliary block on the top. We'll get round to auxiliary blocks in a minute, but there's the contactor. There's a cheap Chinese one, Brian and IMO. An ABB one who do a very unique design on the front. You'll see they all move in like that. There's another GV2. There's the Schneider contactors. Old style Siemens. That is an old style Telemechanique one. Then you've got like Allen Bradley ones, which are really, really expensive. There's an overload on the top. They can all look like different things, but you'll start to see, look, between these 3, they all look very, very, very similar because they've got some big contacts, some little contacts, some looking off. Let me tell you what they are and explain them to you. With contactors, they all perform one job. Yeah, they've got to deal with the power. Where are they? They're here. They've got to deal with the power that goes to your motor. That's what they switch in. Now, switching the 3-phase that goes to motor. So commonly, you'll find they have 1, 2, 3. These first 3 terminals will be reserved for the motor. This is a terrible contact to show you on. Let me find an easy one and do this again. Here's a better one visually, but they're all the same inside. It's just that people have got different styles, yeah? This is a Telemecanique one that then became Schneider, but I'll always know them as Telemecanique. On the top and at the back, you'll see there's these 3 big terminals. This one, and this one. And on the top, at the back, you'll see these 3 big terminals, yeah? They're for your L1, your L2, and your L3 for your motor. They go in there on the top. They then pass through the contactor for a set of double contacts. I'll draw that on the board in a minute to show you. And they reappear at the bottom as L1, L2, L3, whatever, on these big terminals here. They are your L1, L2, and L3 that goes to motor. They are for the power switching to the motor. But to be a contactor and be useful as a contactor, you have to have a couple of other little bits and bobs on here, which are on these front terminals, which I'll show you now. First of all, you're always going to have A1 and A2. They're the coil. When you put the voltage to the coil, whatever voltage the coil is, that is what brings the contactor in and energises the big power contact. So you put voltage onto A1, A2, it pulls the contactor in, and it makes these 3 switch to these 3 and let the volt through, which is really all you want it to do. So that's got to be on every contactor. You've got to have a coil. That's what makes it a contactor. However, on a lot of contactors, you will always have a normally open auxiliary contact, and these particular ones have a normally closed auxiliary contact. You've got both. So what I've got on there is an A1, A2 for the coil, a normally open contact, a normally closed contact. The difference between the contacts is the auxiliaries is they are not capable of switching the power that these can switch. They are just switch indicators that tell you the location of that, whether it's in or whether it's out, and the normally open one is required for doing what we call the hold in. So I've just picked another at random, which is this one. You'll see this one's a little bit different. So clearly on there it says L1, L2 and L3 or whatever. They're the main contactors. This one that's marked 13 and 14, that's your normally open contact auxiliary. It's not capable of switching what these can switch. And then the A1 and A2 are on the top. But it's got all the same things. Well, has it quite? This one hasn't got a normally closed. So yeah, can't do as much with it as that one. But it's got the power contacts, the coil, the normally open, and it's all there. It's just the same thing. Every package is different. And you'll notice that when you look at the packages, a lot of these numbers tend to stay the same and do the same thing. But get your hands on contactors, feel them, look at the drawings and that, and you'll see they have to have the power contacts, a normally open, and a coil. That is the minimum requirement for a contactor. Just to really sell what each one of these contactors is for you, I've got this big comedy contactor. Look back on my old YouTube videos, you'll find 2 videos called All About Normally Open, All About Normally Closed. And I cover this in detail there. But just to show you, look, beneath the lid of this contactor, you'll see there's some huge contacts there. They're the power contacts. They're what are switching your voltage. And on the side here, you'll see some little contacts that move when it moves, look. And they are what are called the auxiliaries. They are for doing your indications and telling your contactor where it is and what it's doing to your auxiliary system. So all contactors have the power contacts that are big chunky bastards like this, and the auxiliary contacts that are little flimsy ones like this. And that is all you need to know about a contactor, I would hope. That enables you to switch your motor, but you also want to be able to switch it on and off and protect it, which is something you don't want to be involved with. That's why you get overloads. Here's an example of an overload. That is currently in the opposition. You can turn it on and it'll let the power through. In there could be magnetic and thermal overloads, like fuses that are resettable. And when either one of them on any of the phases detects that too much current is passing through, as per the setting on this dial, it just trips off. That's as simple as it is. There's another type that I like, the Telemecanique one. Again, they're easy to see. You'll see on the top, it looks like the contactor. There's 3 contacts where the power goes in. It goes through the overload if it's switched on, and it comes out on the bottom. There's a little dial on them usually to tell you what the amp is. And then on the top there, again, you've got auxiliary blocks. So these are 2 little switches. One's normally open, one's normally closed. And they'll be in a certain arrangement when it's not tripped. And when it does trip, it'll put that arrangement out for you to use for control purposes. So with the overload, when it detects overcurrent, so say that little dial set to 4 and it's going at 5, it'll ignore the first bit of overcurrent and then eventually it will trip it off. It also provides phase loss protection, because if any of the phases, the 3 phases that are driving the motor around, are lost, because that phase gets lost, the other phases have to work harder, so it will overload. So if you lose a phase or 2 phases, it'll trip because the phase loss is recognised by the overload protection. And if you are actually overloading the motor and it's taking more than it should be doing, it'll trip anyway. So that gives you all the protection you need so your motor doesn't cook itself or burn itself, whilst also providing some auxiliary things which we've got to go into, because these auxiliary things let you know what this is doing somewhere else. Likewise with the ones on here, there's auxiliaries in here to let you know what something's doing elsewhere else. So every doll starter will contain the overload and the contactor, and they are the bits that you need to make it work. It's in the edit me, which means I've made a mistake. You notice I'm wearing the same shirt, but the t-shirt's different. One thing I got to mention is with a doll starter, it requires manually dependent reset after a power loss. And I forgot to say this in this video, so I'm going to say it now. If you've got a drill or a lathe or anything that's using a doll, if the power is lost, the doll will fall out and it will stop providing power to the motor because there's no power there. When the power reappears, it won't just come back on. You'll have to go and press the start button again. So phase loss, voltage loss, a non-automatic restart is one of the bonuses of a doll. You can wire them so they don't do that, but I'd strongly advise you think very carefully before you do that, because that is a very specific requirement. But generally, if you're using a drill and the power goes off the building, when the power comes back on, the drill won't start turning, or the meat mincer, or whatever nasty bit of kit you've got on the end of your doll. So just be aware that is a thing. Do you know how incredibly hard it is to light yourself in a studio and light a whiteboard? Anyway, let's cover the wiring diagram for the overload and the contactor as they'll appear on the drawing. First of all, we're going to draw the overload. I always draw them like this. And then within that overload, you're going to have the bimetallic strip bit, which looks like that. And you're going to have the amps, overload amps. So you've got a picture of a bimetallic strip that looks like that. Then you've got the overload part of the amps. What's going to happen then is you're going to have the buzz bars across the top, and they will come in to your overload like that. So hopefully that drawing should show you that you've got a set of buzz bars, L1, L2, L3, and you tap off into your overload like that. Your overload will have some kind of actuator on it, and it'll actuate them. It will also actuate, dotted lines mean actuation, a pair of contacts which we've got here, and we'll show them like that. One normally open and one normally closed like that, and the dotted line goes through them to indicate that there's your overload and there's your auxiliaries. Remember, these are switching the power, live 1, live 2 and live 3, and these are the auxiliaries on the other side of that. Let's look at the next bit, which is the contactor. You can have some cables that come down. Your contact's going to show some power contacts, normally drawn like that. Yeah, you're going to show that. There'll be a dotted line through it, then there'll be a coil, maybe shown like that. They'll connect to that. They'll then connect to your motor. You can look at the drawing I'm providing on the screen if this is a bit rubbish. What we're saying here is, when this coil actuates, it pulls these power contacts in, but as you already know, on a contactor, we're again going to have a normally open contact and a normally closed contact, which are our auxiliaries, which are pulled through as a wanner. So that's the whole power side of the contactor covered. The phases coming in, the supply, the protection for the motor and the phasing, the control, which is the contactor, and the load, which is the motor. So every time you're doing something like that, you've got the supply, the protection, the control, and the load. Every single time those rules apply. So now you can see how the power gets through, which we're not really covering in this video much. Let's have a look at the basic wiring arrangement for this doll starter. Let me clean that off. Right then, this is the control side of things. You've still got all the same things going off. Let me show you why. You've still got a supply and you've still got a load. In this case, the supply is the 24 volt control voltage. In this case, the load is the contactor's coil. You've still got protection because the overload is in circuit and the stop one's in circuit, which is a form of protection, but more likely this bit here is your control. So you've still got those four main things you'd expect in play that are on the main side and on the protection side. This is as basic as it gets of a doll starter, and the bit people really struggle with is this bit, the holding contact. Let me take you through it with my finger, because when you use a drawing, you can always follow them through with a colour or your finger. In this case, if the 24 volt supply voltage, which is here, is healthy, then it will go down this leg and it will get to the overload. If the overload's auxiliary contact is healthy, it will pass through the overload to the stop button. If the stop button is healthy, i.e. it's not being actuated, it will pass through the stop button. Everyone gets confused when it gets to here. At this point, it goes nowhere because this start button is open and the holding contact is also open. So that's all it does. If the stop and the overload, auxiliary contacts and stop button are healthy, the power gets to here, and that's where it stays until someone decides to start the motor. At this point, you press this button by applying pressure to it there. That will complete that circuit, and the power will go down there to the contactor coil on the relay. As soon as you let go of that stop button without this bit, as soon as you let go, it would stop. As soon as you press it again, it would start, which, as you're going to see on the video, or may have already seen on the video, that's not convenient. So what we do is, this coil is energising the contactor on the motor, but this auxiliary contact here is also part of it. So you press this button and the voltage goes down here to the coil. As soon as that coil is made, the voltage goes down here and round here and bypasses the stop button. So when you let go of this now, there is still a route for it to get through and the circuit is still completed. Thus the circuit stops running. And at any point, if you overload it, you'll break it. Or if you press the stop button, you'll break it. And that is how the basic Dole starter works. Because anywhere upstream in this area, you can break it and it will stop. And anywhere downstream in this area, you can start it and it will start. There'll be a picture of that up on the screen next. Until you can follow that through with your finger, visualise where all these contacts are and follow it through in its operation with your finger, you'll always struggle. Watch the rest of the video, but always come back to this drawing and understand this drawing. And remember, all your stops go in series and all your starts go in parallel. All your stops are normally closed and all your starts normally open. And on this chain here, there can be loads of things that need to be closed for it to activate. That can be sometimes called the safety chain. But come back to this picture, the drawing's going to be up in a minute, and always make sure you can follow with your finger, or you'll never understand a doll, and you'll always struggle to understand normally opens, normally closed, and why things are controlled like this with normally opens, normally closed. And if you can't do that, you're a fucking dick. That's it for this part. Stand by for part 2. I'm going to break it all down. So this is the first part. Part 2 will be out next week, and we'll pick up where we left off and start looking at how we wire dolls up so that they work. See you later. Welcome back to part 2 of protection and control of motors, where we'll be looking more at the Dole starter and how to wire it. Now we know what all the bits are, we need to know how to put them together. So let's dive straight in and look at some of the options for connecting these up to get different results from our buttons and switches. So every Dole starter will contain the overload and the contactor, and they are the bits that you need to make it work. Let's look at wiring a doll up. Right, I've got out one of my motor test rigs you can use on my motor course, yeah? These simulate just basic motor starting things. So you'll see here, there's an overload with auxiliaries, There's a contactor with some auxiliaries on the top. We won't need them just yet at this point, but there's the basic contactor. And we've got the start, stop, emergency stop, light buttons all over here. So what I'm going to do is I'm going to flip you around. I'm going to take you through a very simple push-to-run motor starter, which you would still need a contact for. You're always going to have a supply. You're always going to have a load. You're going to have some control and some protection in between. So we're going to incorporate the control and the protection into our system. So let me flip you around and we'll just start going through it in little bits. There'll be a dowel drawer in here now. Pause it. Look at that dowel drawing. That is a basic dial and how it works. But I'm going to show you a few different bits and bobs and ways of controlling it on this once I flip you around. To give you an understanding of how it all functions. Just to confirm, yeah, what we're not going to do here is talk about the motor wiring really. We're going to talk about them being a main supply to the contactor and the overload. So the main supply will come in the contactor. This will be on YouTube. Come in from your supply, go through your overload, go through your contactor and go to your motor. We're not involving ourselves in that bit. It's just 3 wires. It comes from the supply, goes through your overload protection, goes through your contactor's control and goes into your load. We're talking about the control side of things. So any white wiring you see on these boards is what would be the mains wiring, and that is omitted because that's just there for show. All we're talking about in here is controlling it using start, stop, contacts, auxiliaries, overload and all that. Let's have a look and we'll go through why things work, why things sometimes don't work, and the way we've got to wire it so that you don't get any problems. Just to explain a few things, yeah. First of all, I've got a 24 volt power source here that just feeds these contact blocks. All my buttons are pre-wired to this loom that's here. So all the cables are pre-wired there. So I'm not going to be wiring the buttons up, but I'll be telling you where they go to. All the 0 volts are linked out. As you can see just here, look. All the 0 volts are already linked out, so I'm not going to go into them. But I'll tell you through the basics of I can make start buttons and stop buttons control a contactor so that it holds in and holds out and push to run and all these other terminologies. So let's go through the doll, how I do it from the start to the end result. Right then, just to set the scene, I've got 24 volts on from a power supply and 24 volts goes to this waggle on this purple cable. So there I've got a permanent 24 volt supply that I can use for my control systems. All the 0 volts as stated, all the blues are 0 volts to the A2 terminals. They're all linked out and done because I don't need to start explaining how you connect up 24 volt negatives. Everything gets a negative, otherwise there's no circuit. If you're struggling with that, you come a bit too advanced. So all the 24 volt goes to here, and we've got neutrals all wired in already. Right, what we're going to do first of all is we're going to make a push to run. A dead simple push to run, which will mean when you press the green button, the contactor will pull in. It will be manually dependent on your finger. So when you press go, the contactor will pull in because the core will be energised. When you let go of the button, it will stop. To do that, I'm going to go for these cables here, and I'll pull out the ones that say push button green 1, which is this one. So let me drag those out. So if you look to the drawing, you'll be able to follow along. If you've got the drawing, screenshot it and put it on your phone, yeah? Here's push button green 1, which goes to that push button. I'm going to give that 24 volt supply, which now means when I press the push button, I'll get a 24 volt supply on the end of this wire, push button green 2. I'm just going to place that into the other side of the coil on the contactor. And now, if everything's well, when I press the button, power will flow from here, down the cable, through the button and energise this contactor. There you go. And as long as I press the green button, this contactor will stay in. As soon as I let go, it will come out. So there I've made a simple push to run circuit, no protection in it, because we haven't covered that bit yet, but all that'll happen is, when you press it, it'll run, and when you don't press it, it won't. That is push to run. It's as simple as it gets for control. Right then, there's no point you knowing, well, you don't know how to do it, you're just watching me, you're going to draw it. Let's assume we'll draw and start like this. The bottom is your neutral, and the top is your live. Don't know why I've put 4 on that, but it's your live. You've clearly got a contactor coil, and that coil is already connected to neutral. What have you got in that circuit? You've got a start button, and that's it. So let's draw it. So now, pause the video here and see if you can draw it. Welcome back. You took a live feed to your open button, and then you took a live feed to your call button. And if you follow it through with your finger, you'll see that the live feed, when it goes through the button, energises the coil. Ta-da! Now then, let's advance a little bit. You always build dual start circuits up from this, so I've got a push to run and it's working. One little thing is, if the power's coming into the overload and going through the overload and through the contactor, when you press this, the contactor will put in, the motor will run. But if the overload was tripped like it is now, yeah, the contactor stayed in. So at the moment now, the contactor's being pulled in, you think it would be running, but it's not because the overload's tripped. Because the overload's got no feedback to incorporate into the device. We'll come back to that later. But at the minute, what we're going to do is, we're going to make this hold in and stop on the stop button. So we want it to stay in there when we do that. So let's make a modification to that now. What I'm going to do, so we don't have to stand there and hold this in, is I'm going to add a contact called the hold in contact. And that works on the fact that at the minute, this is just a contactor being held in by the coil. But when you push it, the auxiliary that's on here is closing. So I'm going to zoom in on this bit and show you what goes off, and I'll just operate the start button over here. So let me zoom into this bit and show you what we do down here and how the hold in contact operates so that you don't have to keep your finger here or ram a matchstick in it. What we're going to do is we're going to utilise this switching itself. So we're going to go to the normally open contact, which is this one. So at this moment in time now, that contact between there and there is a contact that's open. And when the contactor pulls in, it closes. So let's take 24 volts from this block. Just a normal 24 volt feed from this block. And let's take the 24 volts, which is fiddly. Cheers, waggos, through the camera. Now we've got 24 volts into this purple cable. Let's place it into the normally open contact. Like that. And let's think about what's happening. I've missed it. This will get cut maybe. Now let's think about what happens at the other side of that contact, which is where the screwdriver is, when I press this button. So, when I press the green button, the first thing that happens is power comes up this grey cable and energises the coil, which means the coil clicks in like this. And you'll see that clicking in. Also now, power is coming up this purple cable and it's getting switched when the contact's energised and end up with the screwdriver. So that screwdriver's not live at the minute, but now it is. So what we're going to do is, we're going to take a link out of that side there. So we have 24 volts on the end of this pink cable when the contactor is switched. And this will be called our holding contact. So let me screw that in and then we'll talk about what we do with it then. I've now got 24 volts here when this is energised. So if I press the green button, I get 24 volts to the coil and I've got 24 volts on the end of here. As soon as I let go of the green button, the contact has fallen out. If I place this on top of the coil, it then becomes a hold in contact. And when I press the green button, that has stayed in. As soon as I let go of this hold in contact though, it falls out. And again, press the green button, that has stayed in. As soon as I let it go, it falls out. So let me put this hold in contact into here so you can see it operating. Now, we have a contactor that when request is made, stays on. So let me move away and do that. Okay, so now I've wired that switch up, look, so it comes out of the hold or normally open contact into the coil. Now when I press start, the contactor stays in. Cool. Me again. Right, I'm interrupting this video. Let's draw that. First of all, you need to get your original drawing and you just need to modify it for what we've done there. So, have a go, and you can pause it here. I'm not pausing it, you'll pause it. Pause it here and have a go, and then I'll explain what's gone off and how I would solve that problem. Right, what have you actually added? You've added a contact, and the contact is on the contactor. So all we do is we just show a contact, like that, a normally open contact. Give this a name, let's call it K1. That is also called K1, and that means that that coil is the coil for K1, and that is the contact on K1. And all we've done is took a permanent live supply, like that, and then like that, to the coil. But that looks a right old mess. Now, what we can do is we can eliminate some of that. So let's not come off the buzz bar again. Let's make it look a bit more traditional, and you'll get this by reading drawings and putting it like that. And then let's get rid of that scruffy line there. And just put that to there. And now you can see when you follow it with your finger that power comes in off a live, which is not a 4 anymore, goes through the start button, which I now call start, goes down here to the coil, energises the coil, which brings this in, and then current can flow round and get to the coil still. And that's why it's holding in. And all we added was that one contact and a bit of cable. What you'll see now as the next part of the video is there's nowhere switching this off. So let's have a look at that. You fucking prick. The problem now is it will stay in forever because I've got no way of getting it out. The stop button at the minute does not function. So let's have a look at how we do that and the test you do to check your wire don't start correctly. Let me zoom you back out. So just to go over it again, yeah, at the minute, unless I cut the power, which that does, I can start it, it holds in and it stays in. And when I cut the power, I can get it back out. But it's not convenient to keep cutting the power, so we need to now bring in a stop button. Stop buttons are normally closed, and you can have as many as you want in series. So what we're going to do is, we're going to find the 2 cables in the loom for the stop button, and I'll show you how we incorporate it correctly into the hold-off circuit so it doesn't do something that's bad. So I've been in and I found push button red 1, push button red 2. They go through this red button here, and that is a normally closed circuit at the minute. So when we press it, we need it to break the control circuit. We do that by removing the permanent 24 volt from here and put it into another little block. And we send the permanent 24 volts to the stop button. This supply here that's 24 volts is now controlled by a stop button, and we incorporate that back in here. You can follow this on the drawing, which will be at the end of the video as well. Now what happens is, when we press go, the contactor has pulled in and it's held in. And when we press stop, because no voltage is present over the whole circuit, the contactor falls out. The little trick is that when you press go and you press stop, stop will always override go. Right, we're back. This is where you need to draw it. You need to draw it because if you don't draw it, you won't see how it's going off. A load of wires in equipment are just a load of jiggly wires in equipment. Whereas when you draw it, you get nice, straight, easy to follow lines that you can follow with your finger. Now, we have left ourselves a bit short up here, so what we're going to do is just going to get that away. I'm just going to increase the height of that, and now I'm going to go and check that that's still in shot on the camera. Wait there. Yes, it is. Now, that's as it was last time. We've already worked here. I need you to work out where the stop button goes and how it was added and place it in. Off you go, you fuckface. Right, we're back. You only added a stop button. The stop button looks like this. You've got to work out where to put it first. It's going to go here. It breaks the main feed, and you put it in there, and you draw it however you want. In that, I'll draw it like that, look. So that's where the stop button went. So when the stop button activated, everything below here becomes dead. So when the stop button is actuated, nothing can happen. So when the stop was not actuated, the circuit works as before, and when the stop button activated, it's in front of all of the control. So it cuts the throat of everything. You can't operate anything. There's nowhere of a voltage sneaking round the stop button. It goes through the stop button, and that is it. And the stop buttons are normally closed, and the start buttons are normally open. The stop buttons always go in series. The start button's always going parallel. You start seeing the flow. Right, let's see what we're getting onto next. So now we're getting somewhere. If at this point, when you press start, you can't stop it, you've done it wrong. Start should always stop it, and stop should always stop it when it's in. There's one little thing that's missing that we need to incorporate to this circuit, and that's that if it started, which it is, if this was to trip, then the contactor stopped in. We'd think it was running. So now we just need to incorporate this overload into this circuit so that if it's stopped, it stops, and if it trips, it stops, and then we will have completed the doll. So let's just dive back over here. So what you'll find the overload is, there's a contact that's normally open, normally closed. I've used the normally open one, but that means that when it's energized, it will close. Let me show you that by putting a lamp on it. So now, see that red lamp over there? That is off. But when I energise it, it's obviously closed and it's turning the lamp on. So that is acting as a normally open switch. So that is operating, a normally closed switch in the healthy position. So that is operating just like an e-stop. So what I'm going to do is I'm going to take the cables out of it that I've just temporarily used to light that light, and we're going to incorporate that into our circuit so it works in a completely fail-safe manner, and I'll show you how we're going to do that. I ain't showing you shit, you're showing me. So get your drawing that you've already done and incorporate it. What is it? You're only adding one thing again. Don't worry about the wires, you're adding lots of them. It's just a normally open switch, and when it's healthy, it closes. So take that switch and add it in here. Where are you going to add it? It's the overload. When that's not active, nothing should work. What kind of button is it? Where does it need to go? So pause it here, have a think about it, and come back to me. I'll be waiting. Right, hopefully you've got this right. It is a normally closed button. Without it, nothing will work. You don't want anything to work. So what we'd do is, we'd move the stop button down a little bit, and then we'd just add that overload in there, like that. So now we've got the stop and the OL aux. Because, again, like the other button, when that's not there, no power doesn't even go to the stop buttons. When that's not working, none of the rest of the circuit gets power. And that's because when that's tripped, we don't want to be able to start it. And when that's tripped and you go and test the stop button, there'll be no voltage there, and it'll guide you back to change that. So that's where it goes. But again, it's just a stop button. All stop buttons go in series. All start buttons go in parallel. All stop buttons are normally closed. All start buttons are normally open. Do you start to see something fucking coming together here, like similarities keep going on? And I'll give you a clue. If we have to add a start button, we'd add it here. In parallel, like I said, and another. And another. You know what I mean? If you really want to, you can keep on like that. There are different ways of doing it, don't get me wrong. There's a 3-wire way of doing it, but for the purpose of this, as we're just learning, we're going to learn like this. All the starts are in parallel, and they're normally open. And all the stops are in series, and they're normally closed. Start getting that into your head, because that is what is important to know. When you fault find these things, that's always going to be the case. Back to me in the studio. No, not. This is the studio. Back to me in the studio that's over there. We need that to cut the control circuit, even before the stop. So what we're going to do is, we're going to come to this block here, which brings our 24 volts in and feeds our push button red. And we're going to take the 24 volts out of it, and we're going to place it in one side of that switch. So when that switch is now, 24 volts won't go down. We'll put a link in the other side. No, we won't. We'll just take the stop button out of here, and we'll put that in the other side. So we've replaced that connector with the overload, like that. Now, the main 24 volt feed is going through that contact to feed the control circuit. So if this is off, the control circuit won't work. Let's prove that. Right then, you crazy kids. Let's check it out. So now I've got the overload incorporated, yeah? So if I press start, nothing's happening. Why is nothing happening? Because the overload isn't on. So if I put the overload on, which will allow mains voltage to get to the contactor, so the control circuit's voltage is healthy, now I can start it and I can stop it. And if it's running and I hold my finger on the button, I can override the stop. And if I run it, which it is, and I trip it, watch that contactor as I trip it, it's cut its own throat and dropped the control voltage out. That is the dial. It is looking complicated on here, but actually it's a very simple process incorporating a start button, a normally open, a stop button, normally closed, in series with an overload, normally closed, and a holding contact. And these are the things you need to grasp before you start dicking around with dolls. Back again at the whiteboard, yeah? I can't emphasise this enough. If you don't understand how it works on the drawing with your finger and incorporating how these operate and just following it and going, well, it can't get through there, it can't get through there, that's saturated, and get around here. If you can't follow it your finger, you've got no chance of following the control panel. So you need to get a drawing. I'll probably put this drawing up on screen next. This is the traditional doll starters that are on the other video, the video before this. If you can't follow it around the screen, you'll never have any chance of following this. This is the starred out one. I'll put a little screenshot of this up here now. So what chance have you got of following that if you can't follow this? This is not about this. It is not about doing it on here. It's about looking at the drawing and copying the drawing onto here. That's what you've got to grasp. So if you can't follow the drawing, if you think I've missed something, tell me. If not, watch the video again until all this makes sense. The normally opens, the contacts on things, the auxiliaries on things, it all needs to come in, because going inside a control panel is a waste of time unless you understand how each thing functions. You can go, oh, down there, look, overload's okay, stop's okay, stop's there because there's no way of the power getting through. Oh, you press start, it goes down there, da-da-da-da-da. I'm repeating myself, but please remember, it's all about what it looks like in 2D. You can't do it in 2D. And if you can't do it in 2D, you can't do it in 3D. Right, back to me in the studio over there, I think. And that is a dull start and how it functions. Now, what you're probably thinking is, I don't get that. Here's what you need to do, yeah? Before we move on any further with this, and we're going to move on further and look at different things like running lamps, tripping lamps, and all the different things you do to it, yeah? You must understand how stop buttons work, and that they are wired in series and they are always normally closed. You must understand that start buttons exist and they are wired in parallel and they are always normally open. You must understand the concept of how this contact, this auxiliary contact, works with the hold-in contact, and this works. So I'm going to put a simple drawing of a doll starter up after this video, and I'll annotate it with all the bits and bobs, yeah? You need to look at it and do what I call following it with your finger. You will always need a drawing, and you need to follow it with your finger in its different ways it works. And then, when you understand it, we can move on. Watch the video again if you have to. If I've missed anything out, put it in the comments and I'll pick it up in other videos. But that is it. There is no point as moving on to anything a little bit more advanced until you understand this. The holding contact, starting and stopping of a doll, is the fundamental principles of motor control. And until you understand this, you're like, yeah, I get it. I know why that holding contact's there. I know why it breaks the overload. I know why stops go first in the circuit and starts go after. You can't move on because you're just being forever baffled as to why these rules exist. So look at the drawing, watch this video as many times as you need to, put any questions you've got in the comments if it's on YouTube, and understand that. Then we'll start moving on. If you really want to, you can buy a cheap doll starter off eBay, but they're a bit shit. You don't get to open it up like this and do it all. But a lot of that wiring in a normal doll starter would be quite compact. And the drawing, it's all about the drawing. You can follow the drawing with your finger. The thing to remember with anything that says it's normally closed or normally open is, it's normally closed or normally open state is unactuated, how you would find it in the box. That's the important thing to remember with drawings and NOs. For example, the normally open contact on this auxiliary is normally open now when it's off. When you actuate it to turn the power to go through it, it actually closes the contact you've used. So it's not in its normal state, it's in its abnormal state because the other switch is actuated. You need to get your head around that. Like I say, look at the drawing, follow it through your finger, understand the holding contact, and you'll be laughing. So I'll leave this one set up how it is, and then next week or soon I will look at moving on from this one onto adding auxiliaries, getting feedback through things like auxiliaries like this, having lamps on for trip and run and all that. But at its base, many motor control systems operate like this. The underlying principle is here. You've just watched it. See you later, you fucking alligator. welcome back to part 3. Time for some actual electrical content, eh? Welcome, this is part 3 of the motors and controls, starting motors, motor control gear, direct online starting. So far,
previously on actual electrical content.
I'm in my garage, pitch something up. Play cocksucker. We've made a doll. This is powered up now, and if you watch this, look, I can press start. I can't, it's already started. Well, what the fuck's gone wrong there? Oh, it's tripped, look. It won't start the control circuit because it's tripped. That's a feature, not a bug. So if I reset that overload so that power would get through, and I press start, that contact's just pulled in. And when I press stop, that contact's just fell out. And that is exactly what I want to do. Say it was filling a bouncy castle up with air, say it was doing a blower, like your mum. I'd come along, put my blower next to my bouncy castle, plug it in, press start, and it would start, and it would continue to run. So I want to stand there with my finger on the button. If the motor tripped, it wipes out the control circuit, I can see the motor's tripped, and I can stop it. So now, we've got multiple layers on this control circuit, because there's multiple things going off. One thing is, I've got a 3-phase motor, and if we look on this closely in a second, I'll show you where the 3-phase goes in, through the overload, through the contactor, and out to the motor. I'm going to put a drawing up here if this is on YouTube. There's your basic control circuit, there's your basic power circuit, yeah? The motor supply comes in, it goes through the protection, goes through the control, then goes to the load and runs the motor. That layer exists here, yeah? There's just a layer of 415. On top of that, in the last video, we put the control in so we can start it, we can stop it, and when it's started and the overload trips, it wipes out the control circuit because that's what we want to do. Because we don't want the contact to stay in when the overload's tripped and the motor can't run. That is another layer. So now you've got your 415 layer and your control layer on top of it. So on those layers, the 415 layer, which sits here, has the control circuit on top of it that enables the start, the stop, and when it trips to turn it off. Those layers are electrically separate. They don't interact between each other. However, when they get inside components like the contactor, they get mechanically connected up. And that's what we're talking about. The 415 layer, the 24 volt layer, which is the control, don't come into contact apart from mechanical actuations making them do things in between. And this works. Like I say, if you go to the bouncy castle, plug it in, press start, it's tripped, press start, and off your pump goes and blows your bouncy castle up and you're away. So if you was doing this, it'd be fine. You'd know if it was tripped because your bouncy castle would start deflating and you'd be well away. I don't know why I picked a bouncy castle, but there's more than one application for a motor. So let's set in a case, a scenario for this motor control system that's a little bit different. Here's what we're going to do next. We're going to utilise this for a pump. And the pump is in a lake. And the lake is going to be a mile away. So a mile away in a direction from where you are sat now, there is a lake. And in that lake, there is a submersible pump. A cable comes from that pump and comes into a shed. And in that shed is your motor control gear and your supply. So the contactor and the overload are in a shed with a supply from a fuse board. Then the cables go a mile and they go to a pump. That's the scenario we're going to have. Maybe I'll interject here with a picture of it if it's on YouTube, but I'm not going to in this one because I can't be asked to move the camera to the whiteboard. But that's the crack. Same thing applies. If I walk along here and press the start button, now we assume that power is going to the pump and the pump is running. However, we don't know. We don't actually know if the pump's running because of a few reasons which I'll go into now. As I said, the pump's about a mile away. So when I press start, if the pump does start running because the electric goes to it and the pump ends up here in a tank, I don't know if the pump's running because the pump's a mile away. I can't hear it. I also can't see it because it doesn't have anything to see anyway. And if the pipe was a mile long, then it'd take a few minutes for the water to get down the pipe to me. So I've got to basically sit here now, looking at the end of the pipe, or if I can even see the other end of the pipe, hoping that some water pours out. Maybe it will, maybe it won't. But I've got to sit here and wait because this contactor is not here. I can't see it. That could be in the room next door. And this push button station that I'm controlling it from might have been a separate building. So let's pretend the pump's a mile away in that way, the little shed's got the contact and the overload in, but this start-stop system is somewhere on your site where the water comes out. Well, now, I don't know what the fuck's going on because I've pressed the button and nothing's happening. Now, the thing to remember now is I'm a human controlling it. So when I press start, all I've got is, well, I ain't got anything. I can't hear the contact, I can't hear the water. Eventually water might come out, but I've got no visual indication. As a human, I need a visual indication that something is probably running more light than it is now. I've got nothing to look at. And if it was a computer like a PLC, I'd still want some indication, maybe a PLC starting it. And now we're in a whole new realm. So we've got us 415 volt level. Yeah, we've got us control level. But now we're going to add another level, which is the indication. Because at the minute, I haven't got a fucking clue what's going off. If I'm a human, I'm going to use these lamps to give me indication. But these lamps just take a 24 volt supply from a normally closed or normally open piece of control gear on here. So what the important thing to remember is, as a human, I look at the lamp. But if I was a computer, I'd look at the voltage. So a human looks at a visual thing like a lamp or a HMI screen or some sort of computer screen, whereas the computer just looks at a voltage that's going off. But they're both the same. They still derive from a normally open or the normally closed contact. So let's flip you around now, and I'll show you on here how we can add some of those features in so that we get more indication that gives us a better idea if something's running or not running. So this is we've had the 415, we've had the control, now we're going to do an indication layer to either humans or computers, or maybe even a mixture of both. The world really is your oyster with controls. You can do the visual indication on the lamps for me, and the computer indication for the PLC, whatever. It's a very simple example, but what you can actually achieve with all the normally open and normally closed is extensive. Right, let's just get this straight. This is the push button station with the lamps on. That could be anywhere else. That's the contact on the overload. That could be anywhere else. The pump is a mile away, as we've discussed. So we're not, although we're working with it all in a row here because it's easier for filming, these could be in separate locations. If you look down here, the white wires simulate the mains voltage. The supply even, comes in here and goes into the overload. Goes through the overload if it's alpha, comes out of here. Goes all the way around into the contactor and out the contactor to the motor. I will put a drawing of that up next if this is on YouTube, and you can have a look at that. That's the 415 circuit completed. We was already there from the previous videos. Then, currently, we've got a basic doll starter. So they've got a 24 volt power supply coming into here, which is a control voltage. It then goes around through the stop, through the overload and that. So basically at the minute, if we press stop, the contactor stops and the contact falls out. So it's in its not working state at the minute. We press start, the contact pulls in, lets the voltage through, as long as the overload isn't tripped, which would cause the control circuit to turn off. But we're healthy, as overload's good, we can press start and we can press stop. That's where we're at. Now let's look at adding some layers of control to this so that we can see, or the PLC can see things, and it's not as hard as it sounds. It's just simply normally open and normally closed contacts. That's all we're dealing with, and that's the bit you need to get into your noggins. One of the things you need to remember when you're adding in indications is where you feed them from. Because there's no point feeding the power lamp from the wrong side of the contactor, because it won't work. Let me demonstrate that. Let me pull out this white lamp and let's use that for the first thing we're going to do. So all these lamps are just wired to cables. This one's wired to here, look, it just says white pos. So if I put that to a voltage, which is down here, you'll see the white lamp light up. Just coming on and indicating that there's voltage. So what I'm going to do is, from a main voltage down here, which is this little connector block, I'm just going to place it in there. And that is our first indication. So now, when you walk up to the push button station, the first indication you got is that the power is on. Yeah, the control voltage is live. Not the mains voltage, the control voltage. The problem is, if this trips, oh no, it does work, I've wired it right, I've wired it from the right side. So that now indicates that it is healthy and powered. And if there was a trip, it'll go off. I don't want it to work like that though. I want it to be on all the time. So I want that to be on to indicate this power, not indicate that the system's healthy. So I'll rewire that now. And that's why it's important where you take your feed from. So I had to take my feed from somewhere else now, not there.
So the first place I took my 24 volt feed was to this point here. So I'm going to place this white cable in there because that's the first point where my 24 volt feed comes from. So now my lamp should come on, which it has done, or will do when I've got this terminal in. And now that is indicating the presence of a 24 volt supply voltage. And when I press this off now, that stays on. Although it's tripped, I still have 24 volt supply voltage. That's very important because I don't want the trip to take out my lamp, because at the minute, me or my PLC would know my voltage is healthy, but something else is wrong based on other indicators. So, like I say, it's really important where you take your feeds from. So in this case, I want my lamp to say the control voltage is healthy, and so far, it is saying the control voltage is healthy. But if this trips, we don't know, do we? So we need another way of doing that. Let's have a look at that. So the next thing I want to do, now I know we've got a healthy 24 volts light, is I do want to know if this is tripped. Well, I've not got anywhere to find out. So now I'm going to take the amber light, which is here, just check it on the voltage. Yeah. And I'm going to put this into a switch that tells me that it's tripped. Well, on my switch over here, on my auxiliary, on my overload auxiliaries, I've got a spare set of contacts here. So I'm going to put it in there. Let me do that off camera and show you a bit closer. So I've placed that amber into this contact here. So now when this switches, it will switch that auxiliary and bring my lamp on, won't it? No, it won't, because there's no feed to it. So now we need to give it a feed so that it will bring this on when it's off. And again, it's important where we take the feed from. So we need to take the feed from the permanent 24 volts. So no matter what happens, this indicates to that lamp. So let's do that. So we'll take a feed out of this main feed here into that. Because every switch that you're using for indication requires to be fed so that it will lamp light the indicator. There's no voltage there for it to light, so let's put that in. Right then. Now I've got a 24 volt feed feeding that lamp. And I've got a 24 volt feed linked over to this other auxiliary switch so that when I switch this, the amber light should come on. So at the minute it's on, indicating it's healthy. But when you trip it, that amber light's come on. So now as a user or a computer, I can walk over and look at this box and say, well, I've got a 24 volt healthy supply, so my control system is healthy, but I've got an amber light on, indicating I've got a trip. So I can go and reset my trip. And when I reset my trip, my amber light goes off. So already, just with a few simple additions of 24 volt to some lights or some relays, I can tell the status of my control system on this separate layer we've put in, because there's the mains layers, there's the control layer, and this is the indication layer. So now, when I start it, I feel better already because I know it's healthy. But I didn't hear that donk because it's miles away. So now I need to know if the contact's pulled in. Let's add that in. Now, I want to use the lamps to indicate the status of the contactor. Or, not the lamps, a PLC. So I'm going to use a green light for running. That's green. Green is for go. So I come to a contactor, and when this pulls in mechanically, I wanted a way of knowing that. Now, on this contactor at the minute, I've run out of normally open, normally closed to use. But I can have one of these. This is called an auxiliary block. And if you look on the back, there's a little hook that hooks into the contactor. And as the contactor pulls in, it pulls these switches down and activates them. And if you look on the front of it, it's got a normally open that goes through there, a normally closed that goes through there, a normally open goes through there, and a normally open again that goes through there. So this particular one's got 3 normally opens and 1 normally closed. You can get these in different arrangements. And all I do is, to get these contacts to work with my contactor, is when it's in the off position, I slide this on. If you look at that little blue dot there, when I start it, it'll pull down. There you go. So now, I've got additional auxiliary switches. These switches are not capable of switching motors or capable of switching high power applications, but they're capable of switching low-level voltages and currents to give indications to PLCs and lamps. So now, I want to take one of these. Well, when it's not running, it'll be normally open. So let's get my green light, find the cable, and put it in the normally open contact. See what happens. There's my green. I think it should be normally open. So I'll slap it into my normally open, like that. Now, my normally open lamp has got a switch. My normally open contact goes to a lamp. However, I'm sure you've already worked out, there's no supply to the switch. So I'm going to take a supply off this supply, the permanent 24 volt supply, and feed the lamp. So off camera, I'll just disconnect that, and I'll wire it through here. And I'll wire it for a couple more of these as well, so I can use any of these switches to produce 24 volts. So let me just do that, because obviously any switch needs a supply and it ain't got one. But I'm guessing if I put a supply in there, it'll power this cable that goes to my green lamp. Now, I've put a supply to that side of the switch, and I took my green lamp out. You can see it's starting to look quite complicated, but remember, we've already got the 415 volt layer, we don't touch that. We don't touch the dole layer that controls the motor on and off, we're just adding stuff on another layer. This is not, I guess you're sat there thinking, well, how do I do this? Go and buy yourself a contactor and overload, some bits, cables, some lamps off eBay or something, but you can just as easily do this in a drawing. So don't worry that you haven't got all this gear, you can just do it in a drawing. But what I'm guessing now is, if I press go, I'm going to get a green light to tell me I'm running. And I have got a green light to tell me I'm running. And if I trip the contactor, because it's tripped, and because it's interlocked on the mechanical side of it, the trip lights come on, and the green lights run. So now, in various states of running, like now I've reset it, look, it's not started up again. Start it, it's started. Stop it, it's stopped. Start it and trip it, it's tripped. So what I'm going to do, because this is a remote pump, I'm going to add a little bit more indication. So obviously we've got a trip indication, we've got a running indication, and we've got a power indication. What I'd like to do is just add a stopped indication so that we know it's stopped. So I'm just going to take a feed to a normally open. Sorry, I'm going to take a feed to a normally closed, in this case. I'm going to take a lamp out the other switch. You maybe not get it, but I'm going to put the drawings up if this is on YouTube, and you can follow it through your finger. It's just a simple case of the lamps tell you where this is. And where this contactor is relates to whether the pump starts or not, or whether the pump runs or not. And we'll talk about how that's interlocked in a minute, but let me just put power to one of these, and we'll get that stop light running. So we've got full indication coming back. So now look, we've got even more wires, but what you'll notice is there's a red light on. In the case of my identification, that's to tell me, or the computer system, that the pump is not running, that no one is requesting the pump to run, and there's no reason for it to be running. So I get the feeling that it's not running. If I press start, you'll see now I get a green that indicates it is running. Then, what else might you want to know? Well, what if it's tripped? Then you get a double positive, because now it's telling you, not only is it tripped, but obviously it's not running. If I do the reset, it'll just tell you it's not running. And if I press green, it'll tell you it's running. And all that time, the white light's on, so I know there's a 24 volt power supply. What if the power supply disappeared? Well, I'll tell you what happened. The whole thing had just cut off and I'd know there was no power. And when I reset the power, it'd go into the stop position and I can start it again. And it's not that complicated wiring this in, although it can look like it. It's a very simple collection of circuits. That's it. That's your indication layer. Your 415, your controller indication layer, yeah? All it is mechanical switches. It's when the contact pulls in, it pulls a contact. A contact can be normally open or normally closed. And you pick the correct one to light up the lamp. Everything you see that's like the auxiliaries on top of this overload, or these contact auxiliary blocks, is just a switch. Normally open or normally closed. And if you select them in the right order or the right type, you can make it show you things whether you're a computer or a human. As well as that, something else to grasp is, you could take it through one contact on one contactor, then another contactor, then another contactor. So for example, if you want to have a light, say, are all three pumps running, and you had three contactors like this, you could go in with some power, through the next one, through the next one, and through the next one. The world is your oyster with normally open and normally closed, to be honest. So that's indication. There's a lot to go out there. Just remember, humans need indication of what's going off to enable us to run machines. But more than anything else, indication needs to go to PLC so PLCs can decide if it has told a motor to start, has the motor started? If it has told a contact to pull in, has the contact pulled in? And it can just as well do both. It's very easy to wire using the right contacts for a contactor to tell a PLC and the lamp to come on. It's that easy. So yeah, look back over it, look over the drawings, and you'll see the indication and feedback, which is the indication of a PLC, is used a lot in drawings. See you next time, dickhead. Welcome back. This is the final part of this motors and doll starting thing where I'm covering a lot of doll starter stuff. And now we're going to throw in something that's not been there before. We've been talking loads about start and stop buttons, yeah? But what about if your start and stop buttons look something like that? Because we need to get used to the concept that start and stop doesn't need to be buttons. It doesn't need to be a human. It could be a relay or a contact or a sensor, or it will always be some sort of switch, but that switch doesn't have to be operated by a human. It could be operated by a product, a magnet, a sensor, and all sorts of stuff. So let's dive in there and look at what alternatives we've got for start and stopping, but not with start and stop buttons. Hold on, it's going to be a rough ride. And also, in case anyone noticed, this is a makeup shot. I'm filming this about a month after. I've just literally put the same shirt on and hope my beard's the same length. And I think that light bulb's in the wrong place, but there you go. Enjoy the video. One more thing I want to throw on this video is the concept of normally open, normally close. I'm going to throw the stop button and the start button things. You can have as many start buttons as you want in... Go on then, tell me. In parallel. You can have as many stop buttons as you want in series. We did that in video 2. But I use the term buttons. But let's just say you can have as many stop items and start items as you want. For example, in this pump situation here, if there's a tank here and it's topping the tank up that's a mile away, have I got to sit here and do that? Fuck's sake, mate. What is going off with the juice? God damn it. Fucking not on again. You absolute fucking c***. Right, there you go. Got power now. I should have known to listen to water power in. Have I got to sit here and start it and stop it all day long? Because that would be a very, very boring job for me. So let's prove that you can put other things in that be start and stops. So start and stops don't need to be buttons. Because otherwise, we'd have humans doing stuff. They can be just relays that are controlled by, say, a computer, or they could be snazzy buttons. Let me show you. First of all, let me get rid of this fucker because it's right in the way, and let's get something that's a little bit more useful to show that a start and stop button can be other items, especially in this pump situation that we're dealing with now. Oh, fucking hell, where's a fucking ton, mate? Oh. Right, so what I'm going to do is, we're going to make these pump switches control this pump. Now, these switches would be at this end. So the tank we're trying to fill at this end would say, I've not got enough water, start the pump. Then when there was enough water, it'd stop the pump. So we'd have a manual option, which is the push buttons. We'd have an automatic option, which would be these floats. One of the things I want to get across here was a thing like on this overload that normally open, which has brought that little trip light on over there, and the normally closed can sometimes appear to be the wrong way round, because normally open, normally closed are in the normal or abnormal states. And one thing with this that you need to be aware of is that if you want to play with the rig like this or do floats like this, you have to be aware that there's a process value in. I thought I'd just not recorded this then. There's a process value in there, or a process, what the fuck am I on about? I'm trying to say, basically, let's get this right this time. With these floats, there would be water. So obviously you'd want to turn it on when it got low. This is the low float. And you want to turn it off when it got high. So some people do this. On. Off. That is wrong. If you think about how water operates, you'll know why that's wrong. It doesn't go on, off. It does this. The water will rise. This float will go on and it will stay in that position. And as it rises more, it will take that up and say off. And as the water drops down, it will come down like that and do nothing. And it will come down like that and do something. So let's think about the pump running with the water just go through that process. So in this case, we're trying to fill a tank at this end from when it's empty to a set value. The empty is down here and the set value is up here. So if we imagine the pump is not running and we manually start the pump because the tank is empty, what would happen is water would come in and lift this float up. And at that point, nothing would happen because we'd manually start to fill it. That's not the full one, that's the low one. Then as the water rose and rose and rose and rose, this one would go in and the pump would stop. However, the float would stay in that position because eventually the water would naturally come out of the tank and it'd come down, nothing would happen, and then the water would come down the tank, down the tank, down the tank, and then it would start again. Then water would get pumped in and nothing would happen, and it'd fill up and it'd stop, go down, it'd start, go down, it'd stop, whatever, you get the idea. You've got to think like the water, yeah? So call me stupid, you can. If I'm not mistaken, this one will tell you it's low and it will start the pump, but it won't start the pump there, it will start the pump as it drops. And this one will stop the pump, but it won't stop the pump there, it will stop the pump when it does that. So now we need to work out in what positions they are needed to operate to do what thing, and then get the normally open, normally closed correct, because these are capable of doing normally open, normally closed. So which ones start and which ones stop? That's a start. And that's a stop. So let's make a note of that. Right, so what I've done is I've gone away and checked my working out. Maybe what I said before was shit. But what I'm saying is when this float goes upwards, it's the stop signal. And when this float goes downwards, it's the stop signal. Well, stop needs to be normally closed. And start needs to be normally open. So now what I need to do is go down here to these terminals that are the wires coming from these and find those contacts for each one with my multimeter, which I'm not going to show because it'll be fucking boring. But then I'm going to show you me wiring it in to do, I just burped, to do the automatic bit. Let's do that. I'll get that all prepped up. So I'm not going to show you, it'll be boring. They're just switches. It's a little bit complicated because they floats. Yeah, if you want to do it for real, these floats cost me £3.50 off eBay for the pair. It's fucking ridiculous, mate. So if you are thinking about knocking some of this up, it's not prohibitively expensive to buy a shitty second-hand 24-volt contactor and all your gubbins, yeah? Anyhow, just one other thing. So I'm using this shop and test today, and I used to bum flute test leads, yeah, so how fucking great they were. I'm not being paid for this. This is just a genuine thing I've just noticed. Honest. They paid for this office. Get over it. I used to bum flute test leads. And I never thought, I don't think the Chevron ones are as floppy, but you see how thin they are. Yeah, not many test leads are made that thin that they'll just go into terminals. And they will, which is good. Because normally to fuck around shaving up, but they will actually fit in there, which is nice. So, stick that in continuity. You could probably hear that beeping. I'm going to test this one now. This one wants to be a normal open, so if I go in the common. Oops. That's close. I'm going to do this off camera because it's just me testing things. It's fucking boring. I'm not trying to show you how to test a probe. I'm trying to show you how to wire a alternative start and stop system up and watch it work. So I'll be back in a minute. Right then, I've wired this start one up. I've got the right cables so that as it falls, it makes the contact. That is just the same as you pressing the button. Although that ball didn't fall then. So now, this acts like a start button being pressed when it gets to its lowest level. Like that. Let me show you the stop. As you'll hear, this is currently normally closed. And as it rises to the top, it opens like a button. Stop. Stop. And if we remember, the water's going to come up and activate these in a certain way. But when I do another take, this is beeping and get on my tits. Good beep though. So they're wired in now. I've used the pink ones at the minute are from a start. And the blue ones are from a stop. So all I've got to do with these alternative push buttons is wire them in series and parallel into the start stop circuit, which I'm going to do. I'm not going to show you how to do that because I've said on every fucking video I've done, you just put the stops in series and the starts in parallel. Like, if you can't work it out, draw it, because drawing, following it with your finger, is how you'll learn. But let me just wire it and show you the alternative, because the next video I'm going to do, we're going to get rid of these because these are a pain in the butt, but I'll come to that in a minute. Right then, people, hopefully you're following along at home. Hopefully you can just see, if I move you that way a little bit, you can see the box. Now, if I press the stop, I can stop it because I've wired the stop button in. If I take the stop out, it just starts up straight away. That's because these floats do something that buttons don't do. They're automated. It's automatic now. That's how it functions. So now, if I cut the power, it stops. But if you put it on, it will start up automatically. This is the feature of automatic things, because these switches don't need to be pressed by a human. At the minute, this tank thinks there's not enough water in it. Now, if we pretend to be water and come up like this, up, nothing has happened. But if we pretend to keep coming up, getting full, and it's stopped. And it would stop there. Then as the water got taken out, this one would go down, and nothing happens. And then this one would go down, and it'd start again. And it'd fill up, nothing happens, up, and it stops, and it empties, and it stops. And there you go. That is an alternative to push buttons. Again, just using normally open, normally closed contacts to pretend to be those push buttons. There's a little problem with this. It's a great demonstration, but there is a problem, and I'll show you what the problem is. At the minute, the tank's doing its thing. That's fine. But if I come over here and press start, start won't work because the tank's doing its own switching. Start won't work because it won't, because of the way I've wired it. So the buttons don't work anymore. I can stop it when it's running, and I can start it when it's stopped. But that's because what I've done here now is I've intermingled my manual and my automatic devices, which you don't generally do because it's a bad idea. So what you would incorporate in this is, on this toggle button over here, you'd have one side for manual, one side for the middle would be stop, one side for manual, one side for automatic. It is difficult to incorporate successfully manually dependent push buttons operated by a human with automatic buttons stopped by a process. So there, I'm not going to tell you how it's done, but what I'm going to put up at the end is I'm going to put a drawing up that shows a system that is started. It's not this one, it's not the pump example, it's another example for you to do fastest following your finger firsties. I'm going to put up a drawing that incorporates everything here. It incorporates automatic, although it's by a PLC contact output, and it incorporates start and stop buttons, and it incorporates a toggle switch to select between manual, off and automatic, which is how you'll find the vast majority of things like this are done. So that concludes the 3 parts this little thing. It's 3 parts. This is the last one. But the only way you'll ever be ready for all eventualities, like the off, on, manual, the start, stops, the automatic floats, is to be able to read drawings. So I'm going to make a set of drawings available somehow. If you get your hands on drawings at work, or you can just get some drawings, don't take the proper drawings. Always print out a copy of some drawings you want to work with and work with those separately. Yes, if you want some drawings to work with, you know, somehow I'm going to get a copy of the drawings online, hopefully, somewhere located. Or you can just Google drawings anyway. Or you might have some work, but like I say, don't take the drawings out of your control panels. Always get a PDF, print them out, cut the corner off so that you know you're dealing with a set of drawings that's not related to a job that's being used for practicing stuff with, yeah? I can't go any more than what's in these 3 videos. Everything's covered in these 3 videos. It's just a case now of how you arrange your stop and start circuits, how you arrange normally opens, normally closed to get the thing you want to do. You can have huge change of normally opens, normally closed, and things can get complicated, but generally they will always boil back down to the fact that you've got a dull starter in the process. And if you know that, you can usually work it out. And if you know you've got your different layers of indication, control, and blah, 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 you can work it out. But it's a long one, this is. It's really got to end because this shit can go off forever. You can have pump systems with 30 sets of these that just work. So, yeah, good luck out there on your own. Not really. Take away from this that stop buttons are always in series and normally closed. Stop buttons are always in parallel and normally open, unless you've got some weird control system. Don't quote me on that. All your auxiliaries exist. Auxiliary blocks, auxiliary contacts, relays and that, knowing they have coils, knowing how they work. I'm going to do a video on drawings shortly. It's probably going to be the next video I do. It's going to be like a computer one where I just show you around drawings and show you how to use drawings. The only way you get good at using drawings and looking at control systems from the drawing aspect and following through is to know the basics. Normally open, normally closed contacts, auxiliaries, start and stop buttons. I can't do any more than that except do a video on drawings, which I will do on this channel before the end of the year, just to wrap it up as this series, because after next year I'm not going to fucking bother doing videos every week, but that'll be there. So yeah, you've got to get them out. There's no quick solution. There's no hints or tricks or hacks. You've got to look at stuff and understand how it works, and look at drawings and understand how they're drawn. And in fairness, like, I don't go to every job I do and just fucking work it out straight away. Sometimes I draw it out, sometimes I get it wrong, like I've done a few times in this video. Sometimes I have to get the drawings out and look at them. Sometimes I work out it's meant to be made. It's not a shortcut, There ain't no one out there just fucking does it off the back. Normally it's the drawings and that. And so, yeah, don't feel downtrodden when you're starting. But once you apply the basic principles and stuff, you can pretty much work on your motor circuit. Anyway, fuck off now. I'm going to smoke a pipe. See you later.